really like the title.
Yeah, that's a part of the paper I did not do.
I think it's really like.
Yeah, so now you know the question should to ask, which I not know the answer to. So that's the question.
Very good. Oh, you are again? Yeah. Ya había sido. No, Pablo. Okay, so I think we can start the afternoon session, or well, the second part of the afternoon session. And it's my pleasure to introduce Rangel Lara, who's going to be talking about neutron stars, cuckoo's eggs, and LIGO gravitational waves. So thanks very much.
Okay. All right. Thank you everybody for coming to my talk, and thank you for giving me the opportunity to present this work. This work has been done in collaboration with Joachim Koch, Toby Opferkuch, and William Shepard, and this is the reference number. So we all know that gravitational waves have been a new discovery, a new recent discovery, and it has always happened that whenever we have discovered a new messenger of the universe, we have discovered new things with it, right? I mean, if you think of neutrinos, when neutrinos were discovered, new messenger of the universe, like we discovered neutron oscillations with that and things like that, right? So in this work, which is we try to find out what can we learn with gravitational wave physics and dark sector physics, right? The thing to remember is that gravitational wave physics is basically probing a long-range force, right? Gravity is an infinite range force, and it's a very weak force. So once you know that there is a gravitational wave observation, that immediately tells you that we can probe very weakly coupled and very light mass particles, right? Light mass particles will give you the long range, weakly coupled because G Newton is a very small coupling, right? And this is basically what I'll play with in this whole work. So gravitational wave is definitely a new topic for me, so I'll try to give some of the basics initially, and then I'll show. So the point, the observation that I will be talking about is binary neutron star mergers. We know that LIGO has also observed binary black hole mergers, but that is not the object of my talk. So what is this binary neutron star merger? So this is basically when two neutron stars of appropriate masses collide, produce a gravitational wave, and that's what LIGO had seen, right? And these are the LIGO observations. So what is to be noted is this is the gravitational wave frequency, this is the time, and this is probably the best thing, right? And this is the normalized amplitude. So as you can see, and this is the merger time, this time t equal to 0, all right? This is when the merger happens. So as you can see, the frequency of the gravitational wave signal increases, and it becomes sort of infinite at the point of merger, right? And this was also seen in various different detector sites of LIGO and Virgo. Like from these, from this frequency band, and this I will explain how you get this just using semi-classical physics without using any GR essentially. You can try to find out what are the components of the objects which merged. That turns out to be something like these, around 1.4 solar mass, which is the canonical mass of neutron stars. You can find out how far it is. This you can find from this amplitude of the signal. It's something like 40 megaparsecs away from us. And also, given the fact that you can also find out how much amount of energy has been emitted in this collision. And this was about something like 0.025 solar mass. This is a huge number, by the way. This amount of energy being radiated is a huge number. I'll be frequently talking about something called the chirp mass. This is something which is frequently used in gravitational wave physics literature. This is basically some combination of the reduced mass and the total mass of the two objects. So M1 and M2 are the masses of the two neutron stars. Mu is the reduced mass, and if you add some fraction, turns out that this is a number which frequently appears in the gravitational wave calculation. So that's why people have given that a name. That's called chirp mass, and that is measured quite precisely. And remember, this is just with one experiment, one observation. We have sub% level precision on this chirp mass. This tells you how precise things are, right? And this will obviously improve once you better the detector. Once the detector sensitivity increases, it becomes better. So how do you understand this curve, right? This curve. How do you understand this curve? And it's very simple to understand, if you at least. So the first thing to remember is Kepler's law, right? Kepler's law states that if you have two masses, M1, M2, and their distance is delta, distance between them. And here I'm assuming a point mass, by the way. Here I'm assuming a point particle, so I'm not assuming any structure of the neutron star, which this is an approximation which is correct, as long as the distances between the two particles, the two neutron stars, are much larger than their radius. And the radius is around 10 kilometers, which I'll tell you later. So this is Kepler's law, connecting the angular frequency with the masses and the distance between the two neutron stars. This is the total energy of the system, right? This is again just simple mechanics, right? This is the potential energy, this is the kinetic energy, right? Again, I do not include any internal structure of the neutron star, right? So again, mu is the reduced mass, and these numbers I told you, and this omega is related to this. This is where I call it semi-classical, because this is where GR enters. The power radiated via gravitational wave, and this is something you have to do GR for that, is basically is this number, right? And this you can show by some simple calculations, at least by order of magnitude. Just using order of magnitude and by using dimension analysis, you can get, without using this, you can get these combinations apparently. Not apparently, you can do it, right? So this is how it, and the thing you have to assume is that in this collision, the energy loss of the system is mostly by gravitational wave emission, right? So the total energy that is emitted, the total energy as decreases over time is connected, is basically given out in gravitational waves, right? You combine this and this, you get d omega dt. You combine all of this, you get this. The next point where GR comes in is basically to connect the gravitational wave frequency with the angular frequency of the system, right? As it's and this is basically almost our formula that we know, except a factor of 2, by the way. This is again something which comes from GR. This you need to do GR for it, right? Once you do this, you'll get this signal, by the way, quite precisely. And this was stunning to me. At least I did not expect that. I mean, people have obviously done this, by the way. We just reproduced it. But I always thought that you need numerical GR to get this. But that is only around this region. When the neutron stars are really, really close enough, like for example, when the distance is something like 20, 30 kilometers away. If they are much farther away, you just use this and you'll get the right answer, essentially. Immediately you can get LIGO. Right? So this is the carbon, what you're saying, right? So there's two neutron stars, they're coming close to each other because of gravitational wave interaction. This is what it is. So how does new physics come in? As I told you, that remember, we are probing a long range force. I'll give you the range. And we are probing a weak interaction. So a weakly interacting, very light particle will be probed by these observations, right? Just before that, let me give you some astrophysics numbers just to get used to it. So a neutron star mass is typically 10 kilometers. Radius is typically 10 kilometers. Its mass is around 1.4 solar mass. These masses were slightly lower, but it's around that, 1 solar mass. Not much larger than that. Typically, it's quite old, by the way. Neutron stars are typically quite old, something a few giga-years old. They have immense strong gravitational attraction. That's why the escape velocity is very high, and their temperature is like quite cold. They're essentially, compared to a star, they're quite cold. That's why it's very difficult to see neutron stars, by the way. Right? I mean, stars we can see by eye. We can't see neutron stars by eye because they are very cold. They don't emit enough energy. So they are 10 power 5 Kelvin. So how does this new physics come in? And this is where this plot will tell you basically our whole work. So as I said, assume that there are two neutron stars. And in this work, we assume that there is some dark sector particles, not necessarily dark matter, some dark sector particles, some exotic particles are inside the neutron stars, right? There is a gravitational attraction, right? There's Newton's law. And if these dark sector particles have a long range force between them, right, there will also be either an attraction or a repulsion, given by essentially this formula, a Yukawa potential, right? So where M mediator is the mass of the mediator, delta again is the distance between the two objects. So, and this is the force between the two DM cores, the two dark sector particle cores. All right. So this is how the picture gets modified, right? Now you have an additional force in addition to gravity, right? This will compete with this, right? And in addition to that, this light particle can also be brimmed out, or just think of electromagnetic emission, right? Here we are having gravitational wave emission. You can also have an electromagnetic, sort of dark electromagnetic emission of these mediators. These
kind of mediator masses.
Yeah, I'll come to that. Yes, I'll come to that. And these will be emitted, right? Here where the alpha prime is the coupling. So the change is that in this total energy equation that I told you, now the energy is not only emitted in gravitational waves, it's also emitted in this dipole interaction. Okay, and whether it's a dipole or not obviously depends on how much charges they have. So yes, so this comes to a question. So what kind of masses are we probing, right? So typically LIGO has a threshold of 10 Hertz. That means when the signal enters the LIGO sensitivity, it's around 10 Hertz. Assuming that there's no other force, so assuming there's no new force, typically the separation of the two neutron stars are 700 kilometers. That means when the two neutron stars are 700 kilometers away, they already generate enough new gravitational waves for LIGO to see it, right? That immediately tells you that at least the mediators that you will probe is something of the order of 20 to 700 kilometers, right? That's basically the thing. That's where the force will actually come in by this. And this is the force argument, right? Remember the emission argument can always work, right? But this is the force argument. This is where the force will be modified. So what are the kinds of constraints? So assuming that this new force is repulsive, so there's the first simplest constraint, right? If you have the new force so strong that the neutron stars will not collide, that immediately is ruled out, right? And remember, this range is like probing exotic physics at this range is sort of new. I mean, remember, I'm not assuming any coupling with baryonic matter, with standard particles, right? This is purely happening between the two dark sector particles, right? So this is sort of a new length scale in which we can probe the universe. So first of all, the repulsive forces should not be large enough that the neutron stars do not collide. That's the simplest constraint, right? This is what I'm trying to say, right? There's also the size of the dark matter core. Remember, when I was doing this thing, and this is sort of an assumption in our calculation, when I'm doing this calculation, I'm assuming that this core is actually smaller than the size of the neutron star. Why? Because I'm assuming a point particle approximation, right? So this can be relaxed, but this is something we are assuming this. That the size of the dark core or the exotic core inside the neutron star is small enough. And there's also the constraints from the supernova energy loss. Basically, you can't have any other exotic particles, as was actually discussed yesterday in the Majoran talk, right? You can't have excess particle production with a supernova. Remember, pulsars are produced by a supernova, by the way. So that is also coming into play. What happens for an attractive force? Again, attractive force will attract. So the force must not be strong enough that they'll attract too fast. Right? Again, the 0th order constraint. The second thing is that the attractive force must not be so strong that the star itself collapses to form a black hole, and that can happen, right? I mean, if the attractive force is so strong between the two these dark sector particles. There's also something new that can happen is that the attractive force must not be so strong that these two dark sector cores, say here, will get ejected out, right? Remember, these guys are attracted by this force. The neutron star is attracted by this force. If this is too strong, these can just basically get ejected out, given appropriate conditions. So this should also not happen, because that's not what we are assuming, right? This is also sort of an assumption in our work, right? And the supernova energy loss rate comes in. So how does this thing work? So this is basically one of the main results of our work. So what is being plotted here is the time till merger, and basically here time t equal to 0 is the time when the system enters the LIGO band, right? And here we are plotting the gravitational wave frequency up to some power. That's simply because the curve that you saw, that becomes a straight line, and I'll show you which, and that's why we plotted like this. So if you have only gravity, right, this is what the thing looks like. This dotted line is what the thing looks like, right? And depending on, and remember this is for an attractive force, depending on what is the mediator mass and the coupling that I introduced earlier, obviously the attraction will the merger will happen faster, right? And as you can see, the frequency will also change. And remember, this is the frequency which LIGO measures extremely well, right? So depending on what's the force mediator mass and the couplings, the merger will get faster. This is just a zoom out, like a snapshot of this range, which is not. So this is where the merger happens. Whenever our line reaches 0 in these things, that's when the merger happens, right? So that means if you have 300 kilometers is the mediator mass and alpha tilde prime equal to 1, so the merger happens at something like 500 seconds, whereas the LIGO merger actually happened at something like 1200 seconds, 1250 seconds, something like that, right? So this is basically the constraint. This is basically the observable which LIGO can use. In addition to that, there's also the gravitational wave amplitude, and that is again something which you have to know GR for that. The gravitational wave amplitude goes as omega square delta square. So here again, omega is the angular frequency of the system, delta is the distance between the two objects. As I said, if there is a new force, obviously this will change, right? So this will also, this number will also change, and this is something we can probe this system with. What happens with the repulsive force? Again, repulsive force will slow down the merger, right? So this is pure gravity, this line is pure gravity. Again, remember, this is the time when the system enters the LIGO band. This is when the merger happens, again, approximately around 1200 to 1250 seconds. And if you have repulsive forces, obviously the merger takes longer to happen, right? So you can see that the merger takes much longer to happen. Here also the gravitational wave amplitude depends on the omega square delta square. Now these two plots assume there is no dipole interaction. That means the amount of charges in the two neutron stars are actually equal. I mean, more precisely, you have to take the dark charge to mass ratio, but approximately they are equal. Right? So that's why there is no. This is just the force argument. What happens if we include the dipole argument? This is again the most extreme case where we assume that one of the neutron stars have an exotic charge, the other one has almost no exotic charge. What happens is that here, once the new emission happens, there is faster energy loss, and the merger happens faster. Right? The energy loss is higher. Right? So this is again the same kind of plot. This is pure gravity. As you can see, once you have that, and remember you are just looking at emission, so it's not constrained to be in between 20 and 700 kilometers. You can have much larger distances, much larger mediator masses in terms of lengths. So this is where you can see sort of kink. This is where this kink, say which happens for beta tilde dipole, this thing and this thing, is when this dipole emission is actually efficient, and suddenly the energy loss is faster, so the system merges much faster. So this is how you sort of understand these things, right? Yes, as I said, given that the fact that there is an additional energy loss, the system, the merger speeds up. Yeah. So what kind of parameter space one can look into? Now remember that here we don't get great results as such, but the point is that this is something which LIGO can do for free. And as I'll point out, at least in a recent paper which followed our paper, it showed that something like second or third generation gravitational wave experiments can actually probe sort of the most interesting masses. But let me try to explain what is this. So in all these plots, the x-axis is the dark matter mass fraction, so m chi divided by the m baryon, and this is the y-axis. Sorry, this is the y-axis. The x-axis is the relative strength of the dark force, right? So this is the coupling in the dark force compared to the gn m chi squared. M chi is the mass of the exotic particles. Okay. So these regions that you see, the repulsive neutron star that you see, is something which is ruled out simply because the repulsive force is so large that the two neutron stars will not come close to each other. This is the simplest thing, right? So this region is always ruled out, this region, right? This thing that you see, the low supernova production, is applicable only for the light masses, by the way, it's not applicable for the heavy masses, is basically is the constraint that you cannot produce light particles with which produces a mass fraction the mass fraction which is much larger than this line, simply because then your supernova 1987A constraints will be violated, right? And this band that you see is basically the region where we are assuming that the radius of these dark sector blobs that we see is appropriately smaller, because remember we are assuming even these dark sector blobs are like point particles, right? So in these regions that assumption is violated. LIGO, yes, LIGO, just a naive analysis of LIGO can tell you that this is the region, this alpha tilde prime equal 10 power minus 2 and beta tilde prime 10 power minus 3 is basically the region where anything above is something which LIGO can see, right? So these cases will not work, but something in this case actually will work. And remember, this is with just one single observation, right? And this is the most important thing, one single observation. So for, as you can see, for heavy dark matter masses, LIGO can actually probe this thing. But then comes the next question, like how do you have so much amount of exotic particles inside a neutron star? This is like too large, like 10 power minus 2 or something like that. You can't have it via conventional accretion, and that this is basically this line. This is basically the thing that neutron star goes around the halo. You capture dark matter. This is assuming a local density. You can increase it by a factor of few, assuming a dense thing, but you cannot do that. So this is probably not the most motivated region. However, as I said, it was shown by this paper who are like, I'm not a real gravitational wave experimentalist, who are real gravitational wave experimentalists, that if you go to second or third generation experiments, they can actually probe even 10 power minus 14 mass fraction inside the neutron star, which is actually what is useful in terms of particle physics.
So for heavy mass, you won't have this beige region.
Yes, this region basically goes up. As you can see, it's going up. It basically disappears. Yes, right. So this is the region you're talking about, right?
And the argument to make it, the argument for the beige region, what was it?
So this argument is actually sort of like an assumption in our work. Here we are assuming that the radius of this dark core is smaller than the mediator mass, essentially. And because we are assuming point particles. Beyond this, you need to do some numerical GR, which is beyond
that's
that.
That's kind of for the validity of your
Yes, for the validity of a calculation. This is for an attractive force. Again, basically, you have the same problem here. At least in our calculation, we don't find any parameter space which LIGO can probe. So how do you have so much amount of, and this is something this sort of where the theory is lagging behind the experiment. How do you have so much amount of exotic particles inside a neutron star? There have been two processes which have been postulated in the literature. One is production via neutron decay. So as you all might know that there is some anomaly in neutron decay. Depends on how you look at the decay, I guess. There is some anomaly in the neutron decay. It turns out that if that anomaly is real, then you can actually have lots of amount of dark matter inside neutron stars, right? That can give you something like 10⁻⁻² solar mass inside a neutron star. Also, if you have a star formation inside a primordial dark matter core, that means if you have an extremely dense source like ultra compact mini halos, things like that, then you can have amount of dark matter. Yes. So for now, for LIGO to get to see a signal, it will be a non-trivial physics to find why we have so much amount of dark matter for it. But as I said, in this paper, it was shown that if you go to second or third generation like LISA and Dekigo, you can easily probe this region, which is basically the parameter space to do point. Yeah, this is the same thing. Okay. So yes, as I've tried to convince you, the gravitational waves is a new way to probe the universe. And every time, by the way, we have opened a new messenger to probe the universe, we have discovered something new. This has always happened in the history of science. And this will obviously happen here. These observations will probe a new long-range force because gravity is a long-range force, and will probe also a weakly coupled force, right? Because gravity is a weak coupled force, right? You're coupling, so you're competing with gravity essentially. So as I said, to 0th order, the new force will change the merger time. It can either accelerate it or it can decelerate it, and it will also change the amplitude of the signal. And this technique can actually probe new parts of the parameter space. Thank you.
Thank you very much. Questions or comments? Avelino.
So you only mentioned LIGO in your talk. Can you take advantage of
yes.
Using also Virgo, Kagra, and other?
Yes, yes. So I think okay. When I say LIGO, it means LIGO and Virgo, LIGO Virgo collaboration. Yeah, I'm not trying to.
That's politically not very correct.
Yes. Okay. I'm not in gravitational waves, so I can do it. Yes. So LIGO Virgo. But the point is that I think to get into this kind of parameter space, present detectors cannot work. As I said, if you look at this paper and give you the reference, where they look at second and third generation experiments, and remember, LIGO is the first generation experiment, right? This is only one data point, right? You can actually probe the most, the thing which is motivated by particle physics, the amount of matter accreted by.
Okay.
Yeah. So this is LIGO Virgo.
I have another question there. Passing on to Mario.
Okay, so you mentioned this long-range dark force. Is it acting only in the dark sector or also between dark sector and standard model?
Yeah, so here we are assuming this is only acting in the dark sector thing.
And
here we are assuming it's only acting with dark sector particles because I mean, simply because we wanted to get away from the other standard model constraints. Okay. Right? I mean, if you have a new force between two neutrons, it's very strongly constrained, right? No, there are equivalence principle violation experiments which will constrain, for example, if you have a new force between two neutrons, right? So that's why we wanted to do it dark. But there's no, I mean, we have not yet dark matter, so there's less constraints in dark sector.
Okay. Because I was thinking that if it is a scalar, for example, it's quite.
There'll be problems.
It's to demand a lot to claim that this has not like a Higgs portal to the visible.
Yeah, it can be, but as I said, we are not coupling to the standard model particles.
Okay. Assuming that.
And there was one thing I was trying to say that this need not necessarily be dark matter. This can be some exotic dark sector particles, right? Okay. Simply because if you have dark matter, there is also the problem with self interactions coming in, right? That depends on model to model, but there can also be some self interaction constraints immediately. But those can be easily evaded if you assume this is something like 10% of dark matter, say for example. Then the self-interaction constraints don't really matter too much. So that's why I was explicitly saying dark sector quite a few times. I misspoke a few times saying dark matter, but it's dark sector particles.
I have a question myself.
Yes.
So you keep on saying that this is not necessarily dark matter, but then how does it end there in these quantities also?
Yes. So how does it? So your question is how do we actually have these things?
How did you end up with such a big quantity of something in the dark sector that is not the dark matter?
Yes, as I said. So you're essentially saying how do we have so much amount of dark sector particles inside the neutron star? Right? Is that your question?
Well, you're accreting something, right?
Yes. So
I'm assuming that when you're accreting something, your star is moving in a kind of dark matter halo.
Yes. So that's the thing. So this is part of the dark sector, but not really dark matter. And this is the part, as I said, is sort of the weak part of our paper, because as I said, we do not know how we have so much amount of dark sector particles. At least given LIGO-Virgo observations, we do not know how we have so much amount of dark sector particles inside the neutron star. At least this is definitely not possible via accretion.
My question is, if it is around, it contributes to the dark matter, right? Or
Yes.
not?
Yeah. If it contributes to dark matter, then it's very difficult, because as I said, this is beyond the no accretion.
Okay.
But we can have this via, as I said, via this neutron decay, say for example.
A neutron decay. Oh,
Yes.
right. Okay.
So,
Brilliant.
yes, you can
Yeah.
have that,
No,
but,
I get
but
you.
yes, that's why I'm saying it's not conventional dark
No, I
matter.
get you. And another question is, imagine that it was dark matter for a minute, okay?
Yeah.
Does this kind of long range interaction mess up with structure formation at any point?
Yes. So this is again next question. So remember, structure formation is. So I think it's easiest to think of this in terms of self-interactions, because that messes up structure formation, right?
Yeah.
And self-interaction is valid only if something, all these constraints, this 1 centimeter square per gram is valid only if the particles make up 100% of dark matter. So if you think of all this double disk dark matter, which is basically 5%, then I think all these constraints are ruled out. All these constraints do not matter.
If you're playing that game, then you also have to assume you're moving into a subdominant kind
Yes,
of halo.
yes, that's what I'm saying.
So it also affects your accretion. But yeah, I
yes,
understand where you're going.
yeah.
Okay. Thanks very much again.
Okay,
yeah.
thank you very much.
Thank you very much. Oh, hell yeah. All right, so our next speaker is Luca Vicinelli, who is going to be talking about the quest for actions. All right, thanks very much, Luca.
All right, great. Hi, so welcome everyone. Thanks for the opportunity to talk here. My name is Luca Vicinelli. I'm a postdoc at Uppsala University and Norvita Stockholm. Today I'll talk about the quest for the axion within the quest for new physics at the conference. So, my outline is to briefly mention what the QCD axion is and how it's produced cosmologically. Then I'll talk about axion mini clusters, what it means in terms of the detection, and then I'll skip into axion stars. Well, we know that dark matter is present fundamental component of nature. For example, here I put the all-sky lensing map, which is the integrated column that you infer from the Planck 215 data. This boosts the search for what this component is. For example, here I've put the MSSN golden region, which is yet to be explored or completely closed up before we end up detecting the neutrino floor that we heard of yesterday. So, like the supersymmetric particle is a possible candidate for being the dark matter. Another candidate could be primordial black holes. We have a tiny window here in which you can dream of fitting your inflation parameters in order to create the amount required. There are other candidates like sterile neutrinos that are been revived recently, and we also have axions as a possible candidate. So the axion is basically hitting two birds with a stone, because it was originally included in the standard model theory to cure a problem with within the strong CP, the strong sector of the standard model, but it was also immediately pointed out as a possible dark matter candidate, in which the energy density that would serve as the dark matter that we see around is stored in the oscillations of a coherent oscillation of a scalar field. These oscillations that behave and that scale with the scale factor of the universe as matter, as a cold matter component. So it's the energy density is stored in the coherent oscillation of the field. Good. There's been a steady increase in the interest of the axion community. You can see it from the participation in dedicated talks. and conferences in the last 10 years. This is because it's a falsifiable and one-parameter theory. So this is the search for the axion in the next year. Here on the y-axis is the axion-photon coupling as a function of the axion mass. Given a theory for the axion, I can compute this anomaly graph, and then this would give me relation between G and M, which is one of these thin lines. So the axion-photon coupling would be proportional to the axion mass for a given model, and this would lie my theory in this yellow band here, which is a proper QCD axion theory, which is currently being probed only by ADMX in this tiny window here, which is slightly off what we think the axion for dark matter would be. This is because if we think that if we postulate that the axion is a one-parameter theory, then including the additional requirement that we want the axion to be the dark matter pins down a specific region. So we have one additional constraint and one prediction for the axion, for the mass of the axion particle. That also serves as a dark matter. The width here is due to uncertainties in the production. I'll discuss briefly. Okay. Remember that these different experiments postulate or not that the axion is the dark matter. This is, for example, using CMBS4 for probing GA gamma gamma would not require the axion to be the dark matter, whereas cavity searches do. Another way to see this is, for example, looking at the value of the axion mass or equivalently of the axion decay constant, which are related for the QCD axion by an inverse proportionality, as a function of, well, either the Hubble rate at the angle of inflation or the tensor to scalar ratio. So we see that if we want the axion, basically the axion mass is constrained to live within a few orders of magnitude, if we assume that the standard that the axion is not present as a field during inflation. When we open up the possibility for the axion to have a large quantum fluctuations because the Pechet-Quinn symmetry breaks during the inflation, then we can open up the possibility for the so-called anthropic window, although we require extremely low values of the tensor to scalar ratio and relatively low values of the of inflation for this to be accommodated. So, what's the dynamics of the axion? It's the breaking, the spontaneous symmetry breaking of a Pechet-Quinn field, which occurs when the temperature drops below the axion decay constant F, which is inversely proportional to the axion mass. And you have to think of this parameter as of order 10 to the 11 GeV if you want the axion to be the dark matter. Okay, so you have your Pechet-Quinn field that sits at a radius of order Fa, and the axion is the angular variable and sits anywhere between minus pi and pi. At much lower temperature, when the QCD phase transition occurs, this Mexican half potential tilts, and this curvature gives an effective mass to the axion that starts to oscillate about the true minimum. And as I said, it's these coherent oscillations that behave as cold matter. The detail of this tilt are hard to pin down. As you see, this has to be followed by a dedicated QCD lattice computation, and different groups still find different results and don't quite overlap. So this is still work in progress and gives some of the uncertainty that's currently under scrutiny. On top of this, we have a string wall network that's forming. So we have, because of the Hilbert mechanism, we have a string network that forms when the Pechet-Quinn symmetry is broken, if it's broken after inflation. This network would evolve until the domain walls that form dissipated at the QCD phase transition. As you see here, where we put the axion angle, which is the axion field over the value of Fa, ranging between minus pi and pi. Oh, sorry. Okay, we have regions in which the angle winds up around the point with going smoothly between minus pi and pi. A point in a 2D slice of a lattice simulation would be a string. So this is energy density stored in a string that has to get rid. We have to dissipate it because otherwise we would overclose the universe. So this is computationally challenging because the QCD phase transition and the moment of formation of the string network are two completely different energy scales, ranging from the GeV to 10 to the 11 GeV. And we have to simulate all of them. Okay, given that, there will be overdensities that form. There will be regions in which theta is of order 1. This region with overdensities would behave as are basically simulated here by Kolbentach in 1994, and you see they peak at overdensities of order 1, slightly less than 1. This has been recently updated by following them by more than 5 orders of magnitude. This is the difference in simulation in 24 years. As you see, these regions with overdensity would behave as an overdensity for a subdominant field. So, if this were, if the axion were, if we had an axion universe, axion dominated universe, this overdensity would collapse into black holes. Instead, they would collapse into mini clusters at the matter radiation equality. Actually, slightly earlier by the temperature given by this equation, with this density here. So you see from the simulations, if you integrate the power spectrum over the whole lattice as a function of your momentum, or as a function of the grid, that a mini cluster form. So mini clusters form, which are these peaks here at k of the order of the Hubble rate at the QCD phase transitions, but there are much higher power spectrum injected at even smaller scale, or larger k, and these would correspond to axion stars or solitons, as I will discuss later. So the axion mini clusters are the regions enclosed within a Hubble volume at the QCD phase transition. This for an axion corresponds to a mass of the order of 10 to the minus 10 solar masses. Then the density would be fixed by the density at the matter radiation equality for dark matter. This fixes automatically the radius of these objects. So we expect basically a fraction of our dark matter to be into these mini cluster, into these compact objects, and they should have some detectable consequences. One of them could be, for example, microlensing. So structure formation evolves. This mini cluster would merge into halos of mini cluster, and we'll be able to see this microlensing, as you see from the Subaru survey. This is basically the equivalent of the plot for that you see for excluding primordial black holes. We have a fraction of axion which is bound into mini clusters. We don't see these microlensing. This would basically turn it into a bound for this fraction. Axions are bounded into mini cluster of order 10% for the QCD axion to be the dark matter here. The interesting thing is that there are simulations done on a lattice that point at this value of f to be of order 20%. So this would mean that there is a tension between what we see from microlensing and what we obtained from numerics. This could be a potential way to rule out axion, although these two different studies have been done using different techniques, different values of the axion mass, different values of the parameters. This n is the temperature dependence when the axion mass turns on at the QCD phase transition. So a comprehensive dedicated study has to be done for this. But this is potentially a different way to rule out the axion besides direct searches in the microwave cavities. Let's now turn to axion stars. These would be even more compact objects for which the radius is of the order of the de Broglie wavelength. So you have to think of a particle in a box. You have to think of a particle for which the total kinetic energy, and you can see that this is the velocity given by the uncertainty principle, and m is the mass of the star, to be of the order of the self-gravity. So if you solve for this equation, you immediately see that the radius of an axion star would be inversely proportional to its mass. So this is basically a Bose-Einstein condensate which is packed into a region of size r. So it has an intrinsic velocity given by the uncertainty principle with a dispersion of order 10 to the minus 8. Basically the axion community is now focused into the possible detection mechanism or anything that would come out of this type of compact objects. Unfortunately, not gravitational waves, not for the QCD axion. So these are solitons made out of boson. These are oscillating solitons because the axion is a real scalar field, not a complex one. So there is no conserved current, and you have to circumvent that by letting the field oscillate. To do that, we have solved for the Einstein equation with the energy momentum tensor given by the Lagrangian for a scalar field, which is the axion field. And we let the system evolve and find its own metric. So in the non-relativistic limit, the Einstein equation and the Klein-Gordon equation that come out of this Lagrangian turn into the Poisson equation, the system of a Poisson equation plus the Schrödinger equation, which we have then solved with the axion potential, which is not a cosine potential, which is here in red. You see, this is the cosine potential. The axion potential is a bit steeper, the steepness being coming from this parameter c, which is parameterized by the ratio of the up-down walk masses. And the system of Poisson and Schrödinger equation are solved by a shooting method. So we look for the solution of the radial profile of the star that behave smoothly at infinity. So which smoothly go to 0 at r going to infinity. Once we find a suitable solution, the mass of the star is given by the mass enclosed from 0 to infinity, and we define the radius as the portion that enclose 90% of the total mass. We do that for different values of the core density of the star, and we put the values of the mass and the radius into a plot. You can follow this line, for example, in which we have the radius on the y-axis as a function of the mass on the x-axis. So for different values of the radius and the mass, we have a curve, which has one internal parameter, which is the central density of the star. So following the line, following the arrow, we are increasing the inner density of the star, and these different lines correspond to different values of f of the axion mass, or equivalently of the decay constant. As you see, I have rescaled the radius and the mass in units of in proper units in which you can rewrite your system equation, which are 1 over the mass of the axion, or f squared over the mass of the axion. So what we find is basically that the only region that's interesting for us is this line here, which is the R proportional to 1 over m relation that I described before, in which the axion star is in equilibrium because of the interplay between self-gravity and kinetic pressure, which is the pressure due to the quantum uncertainty. When we increase the density, we get to a kink here, which is due to the fact that self-interactions, so quartic self-interaction between axion and axion scattering become important and actually overcome gravity. So from here on, you can forget about the contribution from gravity or the contribution from the Poisson equation. You can just follow what you find from a Klein-Gordon equation without gravity. The problem is that this line here is unstable, so you would never find a star in this configuration here, because you would either, I already spoiled. It would either, if you blow it up, it would go back to this dilute branch here. Okay, and this is the same for this branch here, which would basically explore values of theta of order 1, but this is also unstable because axions in this case become relativistic and the star would just explode. So the only interesting region in which you wish you could find the axion star is in this stable branch here. Just mentioning that there are simulations of structure formation done with ultra-light axions, which are basically particles of order 10 to the minus 22 electrons, so much lighter than the QCD axions. These are not axions that solve the strong CP problem. These are axion-like particles. But the thing is that they form cores inside the galaxies, which can be described as axion stars. So an equivalent system just on much larger scale is found in these structures. So I leave you with conclusions.
Thank you very much, Luca. Questions or comments, please? Mike?
Okay, so imagine you break Petequian symmetry before inflation. Do you expect these axion stars to form, or?
So not from the mechanism that I said, not from the mechanism I mentioned. Okay, if you break the Petequian symmetry before inflation, this means that this network of strings is washed out by inflation.
Okay.
So you don't have any inhomogeneity. And you end up with this situation here, in which you can just pin down what your value of theta would be to have 100% of the dark matter. So given axion of order 10 to the minus 9, so a non-electron volt, you must have theta of order 5, 10 to the minus 3, or smaller. You cannot have a larger value. You have to anthropically choose the value of the misalignment of the angle in which.
And
so
that means.
And this would be smooth between our observable universe, so you wouldn't have this type of inhomogeneities, mini clusters and structure. But nevertheless, you have structure formation, so you can think of having something similar to what people see for ultra-light axions. So you could think of forming axion stars at the core of dense dark matter profiles. But this should be proven by numerical simulators at a much finer grid.
Any other question or comment? What is the number density of these objects, when you're talking about action stars, how many do you expect in Halo, for example?
Okay, so you expect, well, you can think of them, you can think of this like, they have a mass over 10 to the minus 10 solar masses. A galactic halo is 10 to the 12 solar masses. So you expect order 10 to the 22 mini cluster, with each mini cluster hosting one star.
So very, very sparse, right?
Very, yes. So the chance of, depending on the mass of the axion, it would be very rare that the solar system encounters one of these objects. When you do, you would trigger all of these cavity searches, because the energy density in dark matter would be increased by a factor 10 to the 7. Yeah. There are other studies that have basically looked at the stripping, tidal stripping of these mini clusters by nearby stars. Yeah. And this is way more interesting, because you would basically form filaments of denser axions. The density would be not as high, because you would reach over densities of order 10 compared to the local dark matter distribution. But nevertheless, this would mean that you have order 10 higher probabilities to detect these particles because of these streams, which would be much more less sparse, much more frequent to encounter. What else? Yeah, so that would require a dedicated. That's the idea. Instead of doing one cavity search that looks for a specific value of the axion mass, do an array of searches at different masses, which are less sensitive, but you would be able to pin down a wider mass region. This is because of these streams. You nevertheless you get the chance to have over densities that you can encounter.
Okay. Cannot see any other questions, so let's thank our speaker again. Move on to the last talk. I'll give you a 5-minute warning. Okay, so our last speaker of the day is Ricardo Murgia, who's going to be talking about non-standard cosmologies and a general framework for modeling small-scale power. So thanks very much, Ricardo.
Thanks. Thanks to the organizer. I'm very happy to be here in Valencia. So yes, I'm going to talk about this work. Basically, the goal is to provide a simple and direct link between dark matter model building and astrophysical observations. So the point is that we know cold dark matter is cold, and it has a free streaming length that is too small for having an impact on the structure formation. On the other hand, if a dark matter candidate has a larger free streaming length, so if it is lighter, let's say free streaming length of the order of megaparsec, this can have an impact. This has an impact on structure formation. The effect is a suppression of the matter power spectrum with respect to the standard cold dark matter power spectrum. So the starting point is to parameterize this suppression as the so-called transfer function. It is just a ratio between the two power spectra. And the crucial point is that different non-cold dark matter scenarios imply different shapes of the power suppression. So different shape of the transfer function. So nevertheless, typically most of the effort have gone until now into exploring the astrophysical consequences of the case of thermal war dark matter, so candidates that has a thermal momentum distribution, which are a very specific class of models, so they have a very specific shape of the power suppression, which is well described, well fitted by this formula that is typically used for producing the initial conditions for running cosmological simulations. And as you can see, there is only one free parameter in this expression, which is this alpha parameter. So we have a one-to-one correspondence between alpha and so between basically the position of the cutoff and the mass of the candidate. By changing the mass, we change the position of the cutoff, but the shape of the transfer function is the same. So our idea is very simple: is to generalize this formula by having these two more free parameters that are responsible of the shape of the power suppression. So if we want to be more quantitative, we can define this K1 half, that is the scale at which we have a 50% suppression with respect to the standard cold dark matter power spectrum. And so while in the standard approach we have, as I said, this one-to-one correspondence between mass and position of the cutoff, in this general approach, the constraints of on K1 half are the constraint on K1 half or the mass of the thermal candidate are mapped into 3D surfaces in this alpha beta gamma space. So the idea is to sample this volume of the parameter space, and each alpha beta gamma combination corresponds in principle to a different non-cold dark matter scenario, non-cold and non-thermal dark matter scenario. So if we do that, if we sample the volume, if we sample the alpha beta gamma space, we can produce by simply computing the general formula, we can produce all these different transfer functions, these gray ones that correspond to, each of them is associated to one of these alpha beta gamma combination. And for reference, I put also the three transfer functions for the thermal case. And you can see that with the general formula, we can explore power suppression that are shallower or sharper. Basically, the parameter alpha is, even in the new general framework, is still responsible of the position of the cutoff, while beta is responsible of the slope before K1 half, and while gamma is responsible of the slope at a smaller scale. So why do we do this? Because it's not guaranteed that the thermal, the concept of thermal world dark matter is in a certain sense an oversimplification. Most of the non-cold dark matter scenarios are characterized by non-thermal momentum distribution. This is the case for stereo neutrinos from resonant production, so as you can see, the shape of the transfer function is different with respect to the thermal case, and it changes depending on the details of the particle physics model. The same analogous situation for stereo neutrino from scalar decay production, or combination between thermal cold dark matter and thermal warm dark matter and cold dark matter. As you can see, the transfer function is shallower. In all these plots, I'm showing you the solid lines is basically the exact transfer function computed with a Boltzmann solver and with class or whatever, whatever you prefer. And while the dashed line is the alpha beta gamma fit. So the idea is to fit this linear power spectra with alpha beta and gamma, and then to use this alpha beta gamma grid for having a grid of hydrodynamical simulations. So the same is for fuzzy dark matter, and here I'm talking about these ultralight scalars that Luca was mentioning in the end of his talk. And finally, we also fit with we show that we can fit with this with our parameterization also some models, this ethos model that are basically model of dark matter dark radiation interaction. And notice that that our parameterization is not able to fit oscillation like this, so we are cutting them, and this is something that I will come back to this point later. As I said, we have all this, we sample this alpha beta gamma grid, we have all these linear power spectra, we use them for producing initial conditions. So now we produce initial condition not giving anymore just a mass of the thermal candidate, but by giving these alpha beta gamma parameters, and we have a grid of initial power spectra for each of them. For each of them, we produce the corresponding, we run the corresponding full hydrodynamical simulation, and we will end up with a grid of hydrodynamical simulation that we want to use for exploring this parameter space, this alpha beta gamma space, with structure formation data, in particular with Lyman alpha forest. So basically the absorption lines of the neutral hydrogen in between us and distant quasars, which is a trace of the dark matter distribution along our line of sights. And the observable in particular is the flux power spectrum, the Lyman alpha flux power spectrum, which depend on not only on KSZ, of course, but also on our three parameters, our non-cold dark matter parameters, but it depends also on some astrophysical and cosmological parameters. So we have a multidimensional sparse grid of simulations, and we basically interpolate in this grid in order to constrain this alpha, beta, and gamma parameter. So when after we marginalize over the astrophysical and cosmological parameters, we end up with something like this. This is a triangle plot in which this is alpha, beta, and gamma. First of all, if we marginalize over beta and gamma, we can put a constraint on the position of the cutoff, and this is typically this is a weaker constraint with respect to the typical constraint that one obtained with the thermal dark matter analysis. But the point is that this constraint applies to any non-cold dark matter model that can be fitted by alpha, beta, and gamma. So by saying that by writing down this number, we are saying that any non-cold dark matter model, provided the fact that it's fittable with our parameterization, if it displays power suppression at scales that are larger than this, it is excluded at 2 sigma it is rejected at 2 sigma by Lyman alpha forest data. As you can see, beta and gamma, the parameter of the shape, are poorly constrained by current data. But still there is something that we can say. For instance, this cross here corresponds to the thermal wall dark matter case. As you can see, the shape, the peculiar shape of the thermal wall dark matter case is not particularly favored by data. And now we can also say something more. And these different symbols that I'm overplotting they correspond to the models, to the particle physics model that I've just shown. So basically, the idea is, as I show you, I fit the linear power spectra in terms of alpha, beta, and gamma, and then I don't need to run dedicated simulation for each of the model. I just need to pick the region of the parameter space corresponding to such alpha, beta, and gamma combination, and I know if those example models are accepted or rejected by Lyman alpha. And one can draw some, of course, these are just some example models. This is not a systematic approach. We are not scanning systematically the parameter space of the particle physics or the dark matter models. But still, one can say that, for instance, all this, if one look at this, I don't know, let's look at fuzzy dark matter. Fuzzy dark matter as beta and gamma, so the shape of the power separation is always inside the 1 sigma region. So while alpha is not, which means that I can always accommodate a fuzzy dark matter candidate with structure formation data if it is heavy enough. On the other hand, for instance, neutrino from particle decay, they look, it's the peculiar shape. If you see here, they all are these X are all these crosses are outside of the 2 sigma region. So it seems that the peculiar shape of this kind of model is in tension with structure formation data. Now I will briefly discuss 3 potential issues of this approach. One is the fact for fuzzy dark matter models, for instance, I mean, in principle, as Luca was saying, there is this quantum potential, this quantum pressure terms that should be taken into account also during the nonlinear evolution. And while here we are just encoding all the non-cold nature of the dark matter in the initial conditions. Also the small scale oscillations that I was mentioning before. And finally, what about scenarios with a plateau? So scenarios in which only a fraction of dark matter is non-cold. Concerning the first issue, we analyze the scenario of fuzzy dark matter of ultralight scalars. There is this AX gadget code developed by Matteo Nori and Marco Baldi in Bologna, in which the effect of quantum pressure, so the nature of fuzzy dark matter is fully implemented inside inside gadget, inside the code for the numerical simulations. And so we compare, we run simulations by both with the normal code in which dark matter is collisionless, and simulations in which instead all the nonlinear dynamics of fuzzy dark matter is treated carefully. We compare the results, and we see that basically the results are the same. At least for, I mean, this is true for scales and redshift of Lemon alpha forest, of course, and these are the marginalized 1 sigma, the marginalized 1 sigma, 1 sigma, no, I don't know, anyway, these are the two different analyses, but you have to compare basically two different dashed lines and the two different solid lines they basically coincide. So for at least for models in which the whole amount of dark matter is composed by fuzzy dark matter by ultralight axions, it does. I mean, treating them as collisionless doesn't affect our predictions. Then the point of small scale oscillations. This is something that we are working at. We're already, you can find something here, but we are working more carefully on this and more deeply on this also with Maria Archidiacono and the people of Aachen University, with whom we are testing the dark matter dark radiation interaction models. And as you can see here, we fit these models in which we have large small scale oscillation, and we cut the oscillation. And these are we run simulations both with the exact transfer function and with the with the fitted one, so with the one without oscillations. And as you can see, for some of these two for these two models for which the interaction is the strength of the interaction is larger, we have some differences at small scales, while we basically don't have difference for this model. And but the point is that, I mean, we can let's say that we kind of trust our procedure, because these differences show up when the suppression with respect to lambda CDM is already 40%. So these are models that are already very far from data points. I mean, basically, if I test this model or this model, both are very far from data points, both are rejected. So we can kind of neglect them. And in particular, the only model, if you remember the value, the marginalized to sigma limit on alpha that I've shown you was 0.03 megaparsec over H. And here we are talking, we have the values of alpha are these ones. So these are very large. This is another way for seeing that these models are anyway excluded. So if I focus only on the model that is inside the 2 sigma region for alpha, and I plot it here, you can see that basically here I'm plotting the data points. This is the flux power spectra, and for different redshifts. These are the data points of Mike and Hires, the Lyman alpha data points that we are using. These dot dashed lines are the best fit model, and these gray areas are the 2 sigma region by varying alpha in the 2 sigma up to its 2 sigma value. And these 3 lines that you can see here for redshift are almost superposed, and these 3 lines are computed in 3 different ways. One is the flux power spectra computed by running the simulation by using the initial conditions with also the oscillations. The other one is by cutting the oscillations and running a simulation with those values of alpha, beta, and gamma. And the third one is without running any simulation, just interpolating in our grid. So this is, I mean, it seems very, very accurate. Third issue is if we want to face situation in which we have fractions of dark matter, of non-cold dark matter, so plateau. This is the current grid that we have, and the point is that we try to pass from this parametrization to this other parametrization. But of course, we don't want to throw all the simulation that we already have. So what we noticed is that we can map most of the simulation that were characterized by alpha, beta, and gamma combinations in alpha, beta, and delta combinations. And this is and also we are losing. I mean, we are fixing gamma. But as we saw, gamma is basically unconstrained. So basically, we realize that it's probably more useful to have a parameter delta which set the plateau with respect to having two different parameters governing the slope of the transfer function. So basically, these gray dotted transfer functions are the one that we cannot map from one to the other, while all the others are I mean, the blue ones are with the new computed with the new parameterization. The red ones are with the old ones. So the mapping is very good, and we can also, by using this parameterization, we can also enlarge the grid, and we did it, and we have all these new simulations. So now we can also analyze analyze scenarios in which non-cold dark matter is just a fraction of the total dark matter amount. And this is what we are doing, as I said, with Maria and with the Aachen people. So the core message, let's assume that I am a theoretical particle physicist. What should I ask myself? Can I fit my linear power spectrum, the linear power spectrum of my favorite weird, as weird as I want model in terms of alpha, beta, and gamma, or alpha, beta, and delta? And if I can, I don't need to run any numerical simulation for testing the corresponding scenario with Lyman alpha data. Of course, as I show you that I show you just for some example models. I want to do it systematically. I want to scan the parameter space of my model. That's why we wrote a new Monty Python likelihood, which basically, so now this alpha, beta, and gamma is an intermediate step that is used by the likelihood. So basically, I run my class with analyzing, scanning the parameter space of the fundamental dark matter model that I'm interested in, and through this likelihood, the likelihood is able to convert, to translate automatically this alpha, beta, and gamma bounds in bounds on the fundamental dark matter nature. So what we are doing is testing, is applying this likelihood for testing dark matter dark radiation interaction model, dark matter baryon interaction model. But in principle, this can be done for any model which is characterized by a suppressed power spectra, provided that it is implemented inside the Boltzmann solver. That's it.
Thank you very much. Thanks very much, Ricardo. Questions or comments, please? Jose.
The shape of this P of K is completely phenomenological. Or do you have an insight as how it is produced and how it could cover maybe different models? For example, metastable dark matter.
Actually, I mean, the parameter, this alpha, beta, gamma, or delta, whatever parameters are unphysical in a certain sense. So the point was to be very general. So yes, it's purely phenomenological, and depending on the model, they can have a different interpretation, a different reason, a different origin.
Just wondering how you chose the priors for beta and gamma.
For beta and gamma, we chose flat priors in the. I mean, now I think I didn't write any number, but we have a grid of. Basically,
is that between 0 and 10, right?
It's something. Yes, the point are beta cannot be negative, because if you have negative beta, all these things are flipped in the opposite direction, and gamma you can go basically. You can go down to numbers as small as you want, but you don't gain much. But the point is that since the grid is very sparse, we didn't use linear interpolation, but we use this Kriging interpolation method that is not able to extrapolate. So basically, the range of the priors are the range of the grid that are chosen in order to span. Basically, this is more or less the volume for thermal dark matter candidates between 2 and 4 keV, and the idea was I mean, those are the interesting region because lighter masses are excluded, heavier masses are basically not distinguishable with respect to lambda CDM. So the choice is just due to in order to span, let's say, to scan this region.
Yeah, the reason I asked because you show 3 models. One of them had alpha equal to 0.023, but gamma was 10 in that case.
It was minus
10,
yeah.
which means you're at the edge of your prior.
Yes.
This means that you either there's a reason why you can't go above that.
But I mean, these are, let's say, example. We didn't. I mean, this is just. No, there is not a reason why we. I mean, this is just by fitting these three models. Here we were not doing any MCMC. It was just we wanted to check these models. We fit them, and gamma was -10.
Okay, thanks.
Any further question or comment for Ricardo? Otherwise, thank the speaker again and all the speakers in this session.